So today I wanted to discuss this theorem about maximal ideals and fields. So when I first heard this theorem, it felt like it was not intuitive at all. It felt like one of those theorems where the given conditions and the conclusion, there were just like two completely separate things. And at first I didn't see any connection, but after I went through the proof for that, it actually made a lot of sense, and I think it's a very useful theorem. And so let's get started with this. So for those of you who don't know what a maximal ideal is, here is a definition. So R be a ring, and I be an ideal of R such that R is not I. So I is a proper ideal of R. And I is called a maximal ideal if the only ideals of that, the only ideals of R that contain I are I and R. So what that means is that there is, like, intuitively speaking, there is no proper larger ideal that contain I. And then the theorem that I wanted to discuss today goes like this. Let R be a commutative ring. With unity 1R. So it's a multiplicative inverse. And then M be a maximal ideal of R. And I just define a maximal ideal above. Then R, the quotient ring that you can get with this, is a field. So to me, it was not clear at all as to how this is even possible. But a few things that you can notice is, so M is a maximal ideal. So it's not just any ideal. So this theorem wouldn't work if M is not a maximal ideal. You can't just take an ideal of a ring and expect the quotient ring to be a field. That doesn't work that way. But this is a little bit different because it's a maximal ideal. And also here, notice that we are assuming that R is a commutative ring with unity. There are very strong conditions. So if you're just like me, the connection's probably not immediately clear. And the proof that I'm actually gonna show you today contains the first step. I think it's better if I just separate it and then do it as a lemma. So what I'm gonna do is first I'm gonna write down a lemma, and then we're gonna prove that first and then use that result to prove this theorem. So it's like a two-step process. So let's start. So we're not gonna show this theorem first. I'm gonna write down a lemma and we're gonna show that first. So lemma goes like this. Let R be a commutative ring with unity 1R. So notice that this lemma sounds a little bit like this theorem. It's good that they have similar properties because that usually makes it easier to apply. And well, suppose the only ideals of R are 0 and R. So it's either the trivial one, which only includes the additive identity, and itself. The ring itself is always an ideal. Then R is a field. So first, we are going to prove this lemma, and we're going to use this result to show the theorem here. And notice that they have a lot of similar things in them. So they both, this lemma and the theorem both assume that the ring given is a commutative ring with unity, and then the result of this theorem is, saying that it says something is a field. So there's some connection there. Okay, so first let's show this lemma. So we know that R is commutative, and the unity exists too. And since a field is a commutative division ring, commutative and division, commutative division ring, actually we don't need this sign. Let me move this a little bit closer so it's easier to read. So a field is a commutative division ring. And we got this commutative part for free because it's stated in the problem. And to show that it's a division ring, we already know the existence of unity. So all we need to show is that for all x in R, if x is non-zero element, if x is a non-zero element, there exists y, so multiplicative inverse, such that xy equals 1. And since R is commutative, this also implies yx is 1. So we're not gonna prove that. We're just gonna show that xy equals 1. So the way this works is we are just gonna get an element from R and call it x. And we're gonna assume that x is not a 0, because if it was, there really isn't much we need to do. Suppose x is not a 0, then we will consider a set that can be generated by multiplying x from the left side. So it's a little bit like a left coset under multiplication. And we're going to claim that this is an ideal. If we can prove that this is an ideal, it's pretty clear that XR is not just 0. It's not just 0 because R has a lot of elements, including 1. So if it's not just 0, if it's not just that, then we know that XR must be R. That's where we're going. And to show that this is an ideal, first we want to show that XR is a subgroup of R under addition. And XR is non-empty. This part is pretty clear, I think. And then for all XA, XB in XR, XA minus XB equals X of A minus B. And this is clearly in R, so the whole thing is in XR. then by the one-step subgroup test, we know that XR is a subgroup of R. The next one is for all XA in XR, for all B in R, XAB equals X of AB, and this is clearly in R, so the whole thing is in XR. And since R is a commutative ring, we don't have to do the other side. Using these two pieces of information, we can conclude that XR is an ideal. So this is important. So now we know that XR is an ideal. And then XR is not at 0. Going back, I'm just going to draw the line here. So this problem says that the only ideals of R are either the trivial one or itself. And we know it's pretty clear that XR contains more than just 0, because R has unity 1, so x1 turns into x, which is not a 0. So that means XR equals R. And since 1 R is in R, that means 1 R is in XR. That means X inverse is in R. Or that's a little bit. That means there exists Y in R such that XY equals 1. Then Y is the inverse. And now we just proved that every non-zero element in R has an inverse in R. So that means R is a field. So I guess it's here. So let's go back now. So we just proved that if we can show that a commutative ring with unity 1 only has two ideals. One is a set with just 0, and the other one is itself. If we can get that, we know that R is a field. So let's try to apply that knowledge for the first theorem, the one that we wanted to show from the. So for that, we have R, which is a commutative ring with unity, and M, which is a maximal ideal of R. And the tricky part is we're not really showing that R is a field. We are showing that Rm, this quotient ring, is a field. So it's a little bit different because in the lemma, we were given R and we were showing that R is a field. But here we have R and M, and we're showing that the quotient ring that you can get is a field. Nonetheless, let's try to, let me try to move this thing so we'll have more space. Okay, let me zoom in so it's easier to see. Cool. So again, let R be a commutative ring with unity 1, and let M be a maximal ideal. And what we're gonna do is, let's try to actually, since this lemma is what we're gonna use, we might as well just copy and paste this guy under here so that we have easy reference. So to use this lemma, first we want to, what do we want to show? We want to show that Rm is commutative. It's pretty clear that the quotient ring is a ring. If you don't know that part, you want to review the definition of a quotient ring. It's commutative. What we want to show, 1, 2, show, and then Rm has unity. And then the only ideals of Rm are 0 and then itself. And then make sure that this 0 is not an actual 0, but 0 plus m, because it's a quotient ring. So if we can show these three things, then we can use this lemma and then show that this quotient ring is indeed a field. So let's do this in this order. So commutative. This actually comes for free because we assume that R is a commutative. If R is commutative, the quotient ring obviously is commutative. And the unity thing is also pretty easy to prove. I'm just gonna erase this. Unity is pretty easy to prove because 1R plus m acts as unity in this quotient ring for all x plus m in for every element in this quotient ring. 1 plus m, if you multiply that, you get 1r times x plus m equals x plus m. So this is unity. So this is good, and this is good too. The last part is obviously the trickiest part. We want to show that the only ideals of R, this quotient ring, is either 0 or the quotient ring itself. So we are going to do this in a little bit slightly tricky way. So we are going to get, let I be an ideal of the quotient ring. And obviously what we want to show is that I is either just one element, 0, or the whole ring, or the whole quotient ring. And what we're gonna do is, so notice that we haven't really used the property that M is a maximal ideal. We have to use that somehow. M is a maximal ideal, and we haven't used this property. So we're gonna use this. But a little bit tricky, because we're going to create, using this I, we are going to create an ideal in R. So to make it clear, maybe I'm just gonna start like this. And then, so M is an ideal of R. And using I, I'm going to create an ideal of R called I prime. Okay, so oops. And then I prime, I'm going to define this like this. R plus M is in I. So this is sort of like, like expanding I is the most intuitive, And then we are gonna show that, so I'm just gonna go do the outline first before I get into all the detail. But what I'm gonna do is, so we have this I, which is an ideal of R, the quotient ring. We are gonna create a subset of R, just like this. And then we're gonna show that this is an ideal of R. And we're gonna also show that M is actually a subset of I prime. And then this will imply, because M is a maximal ideal, this will imply that I prime equals M or I prime equals R. And then we're going to show that I prime equals M implies that I is just this, or 0 plus M. And then we're going to show that this implies I is just the whole thing. And once we get these two, we're going to use lemma and then show that Rm is a field. So it's going to take a little while, but I'm going to make sure to go through each step. So first, we are going to show that I prime is an ideal. And for that, we need to show that I prime is a subgroup. I prime is clearly not empty because I is, well, okay, I'm gonna show this more carefully then. So I is an ideal. What that means, 0 plus M, which is a zero element, that zero element, this has to be in I. That means 0 is in I prime. So that the first part is because I is an ideal. So it has to have the zero element. And that implies I prime is not empty. I prime is not empty. And then next, the next one is for all AB in I prime, A plus A minus B. A minus B is in I prime. We want to show this. And this is actually pretty straightforward because A minus B plus M equals A plus M minus B plus M. And since each of them is in ideal, is in I, then I is a subgroup, so that means it's closed under addition and subtraction. That means the whole thing has to be in I. So this means A minus B is in I prime. So by the one-step subgroup test, I prime is indeed a subgroup of R prime. And then the second step is for all R in R, for all X in I prime, XR plus M equals X plus M, R plus M. So we want to show that XR is in I prime. Oops, this is a little bit harder to read. So we want to show that for every R in R and X in I prime, XR is in I prime. So if you take XR plus M, X plus M, R plus M, and if you think about it, I is an ideal of R, and then this is an element in R over M. And this is an element in I prime. Not I prime. I'm confusing myself. I. Then, because I is an ideal, this has to be in I because I has this like swallowing property. So now we know that I prime is indeed an ideal. So I'm running out of space, so I'm just gonna again copy and paste this somewhere else in case we're gonna need this in the future. Probably not, but might as well. So we know that I prime is an ideal. The next step is to show that M is a part of I prime. And this is pretty clear. Since I is an ideal, 0 plus M, which is the additive identity of the quotient ring, has to be in M. So obviously this means M is in I. That means, and then for all x in M, x plus M equals M. For an obvious reason, that means M is part of I prime. Because if you look at it, for any element in R such that R plus M is in I, so any element in M, adding that element, if you take a left coset, it's the same as M. So yeah. So we know that M is included in I prime, and now since M is a maximal ideal, we know that I prime must be M or R over M. I'm just gonna delete this because this isn't really that complicated. So now we know that our I prime equals M or R over M. Now, so this and this. So we're gonna show that assuming I prime equals M, I is just M. So we can do this by taking an element in I. X plus M is in I. Then X plus M equals is in I. So, and then we want to show that X plus M equals M. Is this true? And then let's see. So if we go back, oops, oh yeah, it's right here actually. So the way we define I prime, we need to look at this. The way we define I prime is for all, like any left cosets, as long for any R, if the left coset generated by that is in I, that element is in I prime. So this means X plus M, this means X is in I prime. And if X is in I prime, it means X is in M. If X is in M, X plus M is M. That means every element in X plus M is just M. What that means is M is the only element in I. I is just M. The second one, we want to show that I equals R over M. So for that, let X plus M in R M be given. We know that I prime is, oops, I did something terrible there. This is, sorry, this is my bad. This has to be R, because I prime is an ideal of R, and then M is a maximal ideal of R. So if an ideal of R contains M, that has to be either M or R. Sorry about that. Let me quickly fix this. So if I equal, if I prime, these are both I prime. Oh wait, no. This one's good. This one's good. Sorry, I'm confusing myself. This is supposed to be R. Yep. So if I prime equals R, then I would be the quotient group, quotient ring. If I prime equals M, I will be the trivial subgroup. So going back, let X plus M is in R over M. Then since I prime equals R, in R, we know that R is in I prime, because R contains everything. Then this means R plus M is in I, and then I equals R over M. So we just proved the property that is necessary to use this lemma. We just show that this part, the only ideals of R over M are 0 plus M or R over M. So we got these three properties. That means we can use this lemma. We can use this lemma. That means the quotient ring is a field. So we just proved this theorem. Thank you very much for watching, and hope to see you guys in the next video.